Okay, so today in today's session we are going to talk about the digital circuits. So digital circuits are nothing but the combination of the logical gates which are connected and in such a way that given the inputs we get the respective outputs in terms of binary, either in terms of ones or zeros. So it is meant to do some kind of logical operations in such a way the logical circuit is designed. There are two types of logical circuits when we talk here. So one is the combinational circuit and the sequential circuit. Let us switch back to our screen here and let's see here. Okay, so here you can see there are two types of circuits. One is the combinational circuit and sequential circuit. So what do you mean by combinational circuits? We have some circuit here. For example, uh, let me write some simple circuit here. For example, we have some two input and we are adding the operation. We have one more input. We are adding this input with this. I don't know what output I'll get from this, but it's a simple circuit. So it is A, B, and C, which we have taken here. This is Y. So it means this will give A into B operation, and this is performed. So if I just write the truth table for this, so for example, it's a three inputs. So I'll write here A, B, C, and this is A into B, and then there is one more step here, that is A into B plus C. Right. So let us write a few inputs here. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. I'll restrict only for this. We can continue even up to triple ones. Let us see this output. Now for example, 1 into 1 it is 0 into 0 it is 0. Then plus with C I'll get 0. Here the final output. So this is our final output. This is equal to F. And here this is sorry, it's my mistake, it's not 0 0. We will get one output here because it is A into B. So here I'll get 0. So here I'll get 0, but here when I add with C I'll get the output as 1. So here I'll get 0, here I'll get 0. So here I'll get 0 and here I'll get the output as 1. So here I'll get 0, here I'll get 0. It means I'll get the output for, if all the inputs are 0 I'll get 0. If the C input is 1, I'm getting 1 here. So when B and C is 1, I'm getting 1 here. So this is some kind of expression. So if you want to write the expression here, so it means it is A bar, B bar, C. It means I have to take only where there are, the min terms. Min terms means where there is 1. So plus this can be written as A bar, B, C. So like this, I can continue up to triple ones and I can complete my logical expressions. So basically what I want to tell you in this circuit is that now if I give the inputs as 0, 0, 0, I am getting output as 0. It means a combinational circuit is one. The output is going to change with respect to only inputs. For example, if I tell you, let's go to a particular classroom and there is a bench number so and so, there is a book and get it. So what will you do? You just follow these instructions, go there and get the book, right? So likewise here also, based on the inputs and the logic circuit how it is designed, you will get the output. So this is called as combinational circuit. So probably you get only half of the thing right now. So now what is a sequential circuit? Sequential circuits are one, its output depends on input as well as the previous output. It means it takes the previous experience and take the previous and the current input and compute the output. Now let me correlate this with our example. Now I'll tell you, I'll not tell you exactly where table, I'll just tell you go to the classroom, there is a book and bring it. I'll not tell in which table and everything. So what we'll do, you have seen it last time. So that is your memory. So now you will apply your memory and the current input. Current input are my instructions. So I will compute both and you get that book. So that is the, we can relate in this way for the sequential circuits. So sequential circuits uh, can be shift registers, counters, all these circuits will come in the sequential circuit segment. So combinational circuits are nothing but adders. This is a adder, full adder, decoders, encoder, multiplexer, demultiplexers. These are all the examples of the combinational circuits. Okay, so now we will see this part by part. So now we will see the first the combinational circuit, then we will go to the sequential circuit. Is this clear? So I hope I clearly made the difference between the combinational circuit and the sequential circuit. So sequential circuit, for example, the flip-flops or the shift registers, for example, this we will discuss later. Any time have you studied about the flip-flops previously? For example, this, okay, no problem. We'll study here. So this is the flip-flop. It means if I give the one input here, so it will not give just input, so it will use some kind of the previously connected. There will be a feedback here, so based on that, so it will compute and give the output. So these are called as sequential circuits. Okay, so let me save this page here. Okay, so before going to the combinational circuit, let us look into the basic gates. Couple of gates we have seen in the previous tutorial also. Let us revise it. That's not an issue. So first one, NOT gate. So we know what is the NOT gate is. The symbolic representation, it looks like this. This is a symbolic representation of this. So if I give A, I'll get the complement of it, that is A bar. So then if I write the truth table here, so A and the output is A bar. We'll just quickly finish this. 0, 1, and if I give 1 as input, I'll get it as 0. So this is our NOT gate. So AND gate is nothing but it will perform logical AND operation. It means it's something like product, but not exactly the product. It is, we call it as, better to call it as AND operation itself. So the second one is the AND gate. So this you all know it. So if you want to represent this, so there might be 3 input AND gates, there might be 4 input, and it depends, 2 input AND gates and so on. So based on the application, we're going to use how many input AND gate we have to use it based on how many inputs we have. So this is AND gate. So we have 2 inputs here, A, B, and then the output. Sorry, this, we don't write it as C, we'll write it as always YRF. That's the normal way of representation. So Y is equal to A into B. So if it is 0, 0, output is 0. So how do we say this truth table? How do we read this truth table? We'll say like this, the output is 1 only when both the inputs are 1. This is how we will read the truth table. Now this is 1, 0, this is 0. Now it is 1, 1, you see the 1. So it means we are interested only in the output when it gets 1. Now how do this expression came into effect? Now why do we call it as A into B? Because if you look into this expression, so it is nothing but A here into B. That is why we write the output of this AND gate as A into B. So now let us take the OR gate. Let me clear this section. I'll erase this anyway. So let us take the third one here. So OR gate. So take these inputs A, B, and output is Y. So here A, B, and output is Y is equal to A plus B. Right. So it is, we know that 0, 0, 0, 1, 1, 0, 1, 1. So how do we read this truth table now? Now the output is 1 when any one of the input is 1. So this is how we will tell it. When any one of the input is 1, either A or B is 1, the output is 1. If both are 1 also, still the output is 1. So this is how we are going to read the OR gate. Now let us slightly move ahead to the derived gates. Now based on this, we have derived a few gates. It means we can construct, these are the basic gates. Using these basic gates, we can construct any kind of gates. For example, next we talk about the XOR gate, XNOR, NAND gate. we can construct any kind of gates. So that is why they are called as derived and these are called as the basic gates. So this is page 65. So now let me write the derived gates. The first one, this is XOR gate. So XOR gate, symbolic representation, it looks like this. It is basically the complement of the OR gate, like this. So this is my XOR gate. So this is A, B, and output is Y. So if we read the truth table here, so it is A, we have input, and B, and the output Y is equal to A plus B. Sorry, it is exclusive OR gate. It is not an OR gate. What is that? Okay, it's exclusive OR gate. So it's exclusive OR gate. Its equation is A bar B plus A B bar. A bar B plus A B bar. So let us write the inputs here: 0 0 0 1 1 0 1 1. So now here the truth table output is like this. So it means the output is 1 only when any one of the input is 1. So this we call it as XOR gate. Means when both the inputs are same, the output is 0. This is a very important gate we used in most of the circuits. Shreyas, you have any doubt? NAND and NOR gate? We'll come to the NAND and NOR gate later. Okay, so we are talking about the XOR gate. So XOR gate, the expression is A bar B plus A B bar. So if you want to construct this using our basic gate, so how does it look like? Now for example, I have A input. I can construct this using basic gates as I told. So this is my A input. So there is one more, I'll use one more NOT gate. So this is my B input. So I'll use my AND gate now. So I'll take this A bar with B. So now this is my A bar B. I got this. Now I'll use one more AND gate here. So then I'll take from here, I'll connect it. Now this is A into B bar. Now you combine these two outputs using OR gate. So this is the logic circuit equivalent to this. This is a symbolic representation. So I can construct this using basic gates as well in this fashion. Okay. So you can analyze this truth table by writing the A bar into B and then A into B bar separately, then you can add it. So you will get the same thing. Clear? Now let us talk about XNOR gates. XNOR gate is nothing but the complement of this. Page. So next I'll talk about the XNOR gate. So I'll just take the complement for XOR gate. I'll get XNOR gates. So symbolically, for example, I can write in two ways this. So what is this? This is our XOR gate, right? So we have two inputs. This is a two input XOR gate. We have two inputs A and B. So it is represented as A exclusive B. So if I put a NOT gate in front of it, so this will become XNOR gate. So what happens here? So exclusive RB whole bar. So this has become XNOR gate. So symbolically, XNOR gate is represented in this way. So a bubble in the front. So A into B. Now bubble always represents a complement. So now it is A exclusive B whole bar. So when you apply this, so then finally we will get the expression like Y. When we simplify this, we will get it as A bar into B, B bar plus A into B. So we'll see this simplification later. So now let us see the truth table here. So A into B, we have two inputs and we have an output Y. So how does this truth table looks like? 0 0 0 1 1 0 1 1. Now it is just the complement of our XOR gate. So XOR gate, we had 0 here, so now it will become 1. Now there was 0, now this, there was 1 in XOR, and here it will become 0. And for 1 1 there was 0, and now here it is 1. So it means when both the inputs are same, I'll get the output as 1. So this is what it means. Now if you write these expressions looking into this, you say this here. So now the first one is, if I take this first one, then it is A bar into B bar, plus if I take the second one where I got 1, so it is A into B. So this is how the equations are formed. So for the previous case I had not discussed, let me discuss for the XOR gate. Let me discuss for XOR gate. So XOR gate equation was like, let me write the truth table, then I'll come to this. Let me write again the truth table for XOR. So we have A, B and Y which is equal to A bar B plus A B bar. So it's basically 0 0 0 1 1 0 1 1. So here I got 0, here I got 1 1 0. So if you look into the expression, so this is A bar B and this is A B bar. So we'll combine this using plus operator. So then it will become A bar B plus A B bar. So hope you have understood this. So let us go for the universal gates now. Now let us talk about the universal gates. So I'll write here. I told you using the basic gates I can construct any type of gate, any kind of the logic circuit. But the problem is that if I use the basic gates, it will be waste of the resources. How do I say waste of resources? If you have seen the ICs of AND gate and OR gate, basically it will come with a package. It means if I write here the IC, the integrated circuit, so basically it will be having the 14 pins, and internally I'm not sure, they might be 1 and 2 are input and 1 is output. So this is 1 2, these are pin numbers 1 2 and 3. Then likewise I'll have here, then 4 5, then 6 is the output. So likewise I think I'm not very sure because it's been a long time, so you have to check this details, the pin numbers which is input and which is output. But I'm giving you the rough idea, so hopefully it will be like this, that the two inputs are connected. So basically, so this will continue. So the pin number 7 will be grounded here. This will be the ground point, G and D. And this is pin number 8 and 9, and the 10 might be the output. So likewise we have one more here, and get this is 11 12 and 13 might be output, and pin number 14 is VCC for this IC. So basically when we look when we want to use these gates in our circuit design, then there is nothing like individual gates are available. It is available in terms of package. So if I use this IC, for example, I think a 7400 might be IC for AND gate. I'm not very sure. Let me check it. Let me Google it. AND gate IC number. It's 74 series. Yeah, 7408 is the IC. Yeah. So there is a little change here. So 11 is the output. So sorry. So let us come back to our screen. The first two gates are correct, but this is not right. So let me correct this. Let me give the right information. Okay. So here 13 and 12 are the inputs for this AND gate, and 14 is the, sorry, 11 is the output. So likewise 10 and 9 are the inputs and 8 is the output. So this is how it is looks like the AND gate, and the AND gate number is 7408 IC. You can just check it. You Google it, 7408 IC, you will get all the specifications. Now what I want to tell is, now previously we had written one circuit, for example something like this. So we have written, then we have used I have used one NOT gate somewhere here. I have connected these inputs in this way, then I have performed OR operation here. So it means what happens, I have to use different, now I have to use 3 different ICs, but I am not utilizing all the 3 ICs efficiently. Now I used only one gate from this IC, now I used only one gate from the AND gate IC, and I am using only one gate from the another OR gate IC. So it means I am using 3 ICs, 3 integrated circuits to form this. It means I am only partially using this. Now out of these 4, I am using might be only one this, but remaining these will be unused. So that is why whenever we are going for the design of the logical circuits, we do not go in most of the cases by using the basic gates. Only if the number of gates of say NOT gates or more, and we calculate, okay, it comes in one package, then we can go for the basic gates. Otherwise, there is always a best solution is we go for universal gates. So the universal gates we are talking about is the NAND gate and NOR gate. How useful it is, we will see when we go for the circuit analysis. Now let's say it's truth table. Let us say it's a truth table now. So first I will talk about here the NAND gate. So NAND gate is nothing but the complement of AND gate. So if I write symbolically, it looks like this. So it is a AND gate. So in front of that, if I add a NOT gate, so it will become NAND. So that is represented as bubble. So bubble always represent the complement. Remember that. So A into B bar. So this is the equation. So if you look into the truth table, then it is A into AB, and the output is A into B bar. So 0 0, its output is 0 0, sorry, my mistake. So 0 0, it's 0, but its complement is 1. So 0 1, 0 into 1 is 0, but its complement is 1. Then 1 0, it is 1 into 0 is 0, its complement is 1. 1 into 1, it's 1, but complement is 0. It means, how do we read this NAND gate? The output is 1 when both the inputs are 0 or any one of the input is 1, and its output is 0 when all the inputs are 1. Or the simplest way is you can tell like this: when all the inputs are 1, its output is 0. There is another way of telling this. Now let us look into the NOR gate. So NOR gate is the complement of OR gate. So we write the OR gate, in front of that if I write a NOT gate, so it will become a OR NOR gate. So this is A into B. So then I can write this as A plus B whole bar. So A plus B whole bar, so its truth table goes like this: A plus B, then output Y is equal to A plus B bar whole bar. So this is 0 0. 0 plus 0 is 0, its complement is 1. So 0 plus 1, it is 1, but its complement is 0. So 1 plus 0, it is 1, its complement is 0. So 1 1, it is 1, its complement is 0. It means the NOR gate output is 1 only when all the inputs are 0. So this is how we can read this. Okay. Right. So this is about the basic gates, universal gates, and the derived gates. So now let us look into a few examples here. Let me save this page. Alright. So now there are many ways in the examination that may give like this. For example, they'll ask you, given the expression y is equal to a plus b whole bar plus c bar. So they will ask you to design the logical circuit for this given expression. Sometimes what they will do is they will ask this. In the previous tutorial, in the previous session, we have seen simplification of Boolean expressions. So the question will come like this. They will give some Boolean expression. They will ask you simplify the Boolean expression and draw the logical circuit for that. So they may ask in both the ways, with simplification and without simplification. So you should be able to do that. So now think about it. How do we write this circuit? So it's very simple. So first you have to understand how many inputs are there. So we have 3 inputs here. So if it is asked only using basic gates, you have to use only basic gates. If it is asked use any gates, then you can straight away, if you look into this a plus b bar, it looks like a NOR gate. Straight away you can use NOR gate and one NOT gate, and then you combine, the output is done. So let me write both the circuits here. So first I'll write with any gates. So if I write with any gates, so this is my input A and B. So this is nothing but this is my NOR gate. I'll use my NOR gate. So this is A plus B whole bar. Then I use one NOT gate here. So this is a C input. I got C bar. Now combine this using an OR gate. So then I get the respective output. So this is my Y. This is one method of doing. Another method, if I want to use only basic gates, then what I have to do is, so first I have to perform the OR operation. So I'll first perform the OR operation here. So this will give me, if my inputs are A and B for this, so it will give me A plus B. Now I have to obtain A plus B bar. So pass through this with a NOT gate. So NOT gate will give you the output of A plus B whole bar. So I got this. Next C, I have to use one NOT gate so that I can get C bar. So C, C bar. Then I have to combine this with this result. So just combine it using an OR gate. So we'll get the output. So this is my final output Y, right? So this is how you have to write. So I'll give a couple of questions to you. So I'll leave it to you as a homework. So you solve it. So for example, we have Y is equal to A, B, C whole bar into D bar. So there are 4 inputs in this case. I do it. Then we have one more. So Y is equal to A, B bar, C plus A, B, C. Then Y is equal to, you take anything like this, A bar plus B plus C into A plus B plus C. So like this, you can take any circuit and you can do it. Now, before proceeding, I want to discuss one more topic here. Now this is fine, the given logical expressions, and you have to write the circuit. Now there is a special requirement for my circuit. So let me clear this. The special requirement is that, so I'll write Y is equal to summation of, say, 2, 4, 0, 2, 4, 6 for 3 inputs. It means my output should be 1 for even numbers. So this is the requirement. So if this is a requirement, it means the question is given like this: design the logic circuit for the given expression. Now there is no expression right now, so they have given what is the expected output. So first what you have to do is you have to consider the 3 inputs here, that is A, B and C, and then the output Y. We don't know what is the logical expression so far. So just write all the possible inputs here, that is 0, 0, 0, 0, 0, 1, 0, 1, 0 and 0, 1, 1. Let us write this. Complete this table. Okay, so all the inputs, possible inputs we have written here. So now what is it given? So the output is for 0, 2, 4 and 6. It means for only for these values the output should be 1. It means 0 means when all 3 inputs are 0, you have to convert this binary to decimal representation. So all zeros means it is 0. Now this is 0, 0, 0, 1. So this should be 0. And 2 means here it should be 1. And 3 means it should be 0. 4 is 1. And then here 5 is 0. 6 should be 1. And then 7 should be 0. Now looking into this, you can write the expression. So this, and this. Now take all this to write the expressions. So then my y expression will be, then that will be a bar into b bar into c bar plus a bar b c bar. You see this 0 should be represented as a bar, b is 1, so it is written as straight away as b, and c is c, it is 0, so we will write in terms of complement, it is c bar. So plus, then we have the next term is a b bar c bar plus we have a b c bar. So now we will, let me write this properly, this is a b c bar. So now this is the given equation. Now rather than straight away jumping into the design of the circuit, first let us try to simplify this expression to the level whatever we can reach. How to solve this? Let's think about it. How to solve? We have to use all the expressions here. So this is okay. Now let us look into these first term and the third term. So here b bar and c bar is common, and a bar, this is a and a bar. So a plus a bar is equal to 1 from the Boolean theorem. So let us take that common. So let us take that as common. So now I'll take the b bar into c bar as common, then I'll get here a plus a bar plus. Is this common? Anything is common here? Yes, here also there are two things common, that is b and c bar is common. So let us take the b and c bar common. I'll move this table slightly to the right. Yes, let me keep it here. So now then I'll take b into c bar as a common, then I'll get again a bar plus a as now a plus a bar is equal to 1, so I'll get here this is b bar c bar plus b c bar. So what is again common term? So c bar is common, so I'll get here b bar plus b, again it is 1, so it means I left out with only term c bar. Very beautiful. You see this? You see, this is the beauty of the Boolean expressions. So rather than straight away substituting this entire thing into our case, so rather than substituting this entire equation, it means how many gates are required, how many NOT gates, how many AND gates, how many NOT gates, so many things were required. But now nothing. We know we need only one gate that is required, that is one simple NOT gate, and your circuit is done. You see the beauty of this. We need not to connect A and B because A and B inputs are useless in this case. So now if you look into this case, if I put a line here, carefully, then A and B are not an important thing for me now. Now if you look at the output, if you compare with C, now it is just like a C complement. That is what you can get. So now it is a C complement. You give input as 0, I am getting as 1. You give input as 1, I am getting as 0. So that is what it's exactly doing. So this is a very best example that you can look into why we have to go for Boolean simplification, the equation simplification, and how to do it. Hope you all have understood this. A very nice example. In the exam, the questions may come like this, which you have to do it. Okay. Okay then. So likewise, there are quite a few examples. So we have last 12 minutes to wind up the session. You have anything else to discuss? So likewise, we can see quite a few examples. Okay, there might be another way in the examination it may ask. Uh, the other way is that, now this is one method which we have done. So they have given the outputs. Now from the outputs, let me save this page first. So here, these are, what is that y which is given? The y which is given is all output. Now from the output we have constructed our input. Now from these inputs we got our expression, and then we have simplified this. The reverse way is that they will give the logic circuit itself. Let me take a new page here. So here it is given the logic circuit. Like this. We have 4 inputs here, and these are connected to one more NAND gate here. This is A, B, C, T. So this is the output. So if you try to write this, this is A into B bar, this is C into D bar, and this is A into B, let me write neatly, this is A into B whole bar into C into D whole bar into whole bar. So finally it is something like this. It is A into B double bar plus C into D double bar. So we know that double bar is nothing but it is equal to, from the last law that we have studied from the Boolean theorem table. So that is nothing but it is A into B plus C into D. So this is the output. So now they ask you to construct the truth table for this given logic circuit. So how do we do this truth table? So for this you write the inputs as A, B, C, D. Then we have to write an output Y. I'll just show for a couple of inputs. Rest you can construct it. So 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. So now I'll just take these inputs. Now what is this? A into B. Now that is 0 into 0. B into C. 0 into 0. So now if you add this 0 plus 0, I'll get this as 0. Now A into B, 0 into 0 is 0. Now this is C into D, 0 into 0, 0. Now 0 plus 0, it's again 0. Now here 0 into 0, 0. This is again 0. Now in this case if you see 0 into 0, it is 0 plus C into D is 1 into 1, it is 1. So now in this case 1 plus 0, you will get it as 1. So this is how you have to construct the table. So sometimes they will give this logic circuit. They will not give this output expression. You have to find by stage output expression. Simplify this output expression by like this. Then this is the equation you will get. Now for this equation you have to construct the truth table. So this is another way of doing this. Okay. So hope you all have understood this session. So thank you for joining this session.